Dedicated teacher I had actually in this college from 1982 to 1985, MS and MPhil. Professor K.S. Ramachandran, what a fantastic teacher. Okay, he's a very simple man, but he used to teach a lot. Okay, all are dedicated teachers. That's why I could visit so many countries all over the world. I spent 1.5 years in Tokyo as a postdoctorate in Nippon Telephone Corporation's R&D divisions. Okay, after that I visited so many countries in Europe, Korea, again to Japan, Spain, Germany, Italy, Netherlands, Greece, all those because of what I gained knowledge from these institutions. Okay, of course, I'm going to talk about that queuing model. Generally, they speak only that simple model, but this is a little bit complicated models. Okay, so real world problem we are going to discuss. That's what we are interested actually. Sorry is asking what is application. Full applications of us. Okay, so there's only applications related to that I am going to talk. Okay, right. This is joint work with my. They were my student. Now they are working in Welltech. Okay, so still we are continuing the research. They are interested to pursue the research. So we are doing research on Saturday Sundays. We are meeting and we are doing actually. Okay, right. Was Madam Rukmani Madam was a Tangara student, but unofficially collaborated with me. We published several papers. So struggled a lot to finish her PhD. He approached me, then she could complete that PhD degree. Right now, she is not feeling well. I'm sorry to say this one actually. She is very knowledgeable person, okay, but proper guidance was not there. But he joined with me. She could publish a lot of papers in good journals. That's what I said. Of course, sir told I am an associate of 3 journals. One is, of course, Methodology Computing Applied Party, Springer Journal. I am only Indian for that associate editors from India actually. Okay, others are foreigners. Ask me to remove name from that because they're sending so many papers to you. No, you must be, okay, you should continue. That's what they forced me to give that post actually. The second one is Pathology in Computing Applied, the other one is queuing model and service management. It is run by that Taiwan, one of the biggest university. So there also I'm an associate editor. Other one is International Journal of Modern Communication Theories actually. So all 3 journals, of course, I used to review the papers, and this is, of course, because of my work and my students' work. Okay, so Algorithmic analysis of coordinating wireless multi-channel retail queuing network for Finite-Source primary users with admission control of secondary users. So before going to this this one, let me explain geometrically what is the model I'm going to discuss. Okay, this is what my coordinated network queuing models. Look at that. Yeah. Okay. Okay. So we have that multi-server, C servers, server 1, server 2, server 3, like that. It's a parallel servers. Okay. There are 2 types of customers. One is, of course, primary users. Other one is secondary users. He is always giving priority to the primary users because they are paying money to get service. So they are giving the primary users. Okay. So the secondary users are always forming a queue, but primary users are generally finite source of systems. So whenever server is free, you try to occupy this one. Okay. You keep trying. Meantime, this customer also try to get that service. So this is what a cognitive network. It's for both primary users, secondary users. That's the idea of this. They form a queue in front of that. If all servers are occupied by primary users, then the customer may join or may not join. So if you join with the probability lambda into P or yes join here, not joining means leave the systems. So this is what a model we are going to have. Whenever that secondary users occupy the server, the primary user generated, then it will be shifted to head of the queue. Head of the queues, it will be there. So this kind of things are there. So how long he has to wait in the queue and how many are in the, if all servers, all customers are occupied by the primary users, then the new customer generated from the primary users, it will block and move to orbit. This is called Retrial queues models. Retrial queue models, of course, I'm combining with that. Okay, the Retrial queues actually, then the customer from that orbit keep trying in a random order. If any of the server is free, then occupy, or any of the servers occupied by prime user, you'll push that customer to the data of the queue, then you'll occupy the customers. So both way it will actually try to occupy the customers. So this kind of coordinate networks are very, very useful in telecommunication systems. Okay, because the bandwidth is actually wasted by primary users. So to use that fully that bandwidth, we are allowing that use that secondary users to occupy that bandwidth. That's the main idea of this one. So coordinate networks is nowadays playing vital role for real world problems. Okay, so this idea of our work. Finite source retail primary users. I mean that primary users are generated by the finite source. Only finite number of source are there, it will generate. Okay, right. With 3 licensed channels and unlimited buffer capacity secondary user waiting line systems. So I just now showed you in the figure. Okay, right. The infinitesimal generator of the continuous time Markov chain is constructed. That's a very tedious to construct that continuous time Markov chain generator that we have constructed. Once you generate that constructed, the stability condition we can discuss, because we have that infinite capacity of secondary users, we need the stability condition to control that queue. So we are talking about stability condition also. Right? Okay, the joint steady state probability distribution of primary users, both primary users and secondary users, unless I use the matrix geometrics methods. Okay, quite often you are going to use a lot of matrix geometrics ideas here actually. Okay, so several system perform metrics such as such as first passage time to reach the congestion level in secondary users, waiting line, buffer, and its related characteristics are inversion, like how long you have to wait. So, okay, what is the throughput, what is the blocking probability, everything we are going to study for that. Queuing, what is that, the customer who are waiting in the queue. Apart from that, we study numerically results are graphically for that system inside. Next. Model description. So, licensed multi-channel, C channels are there, which I told you, the coordinator of ACL system, transmission systems. 2 classes of users, namely primary users. These are licensed because we are giving the priority to that primary users, because they are paying money to get the service. So we are giving the priority for that primary users. And secondary users, unlicensed users, can dynamically access the channel or transmission of their packet. Whenever the channel is free, then secondary users can occupy to get the service. Okay, that's the idea, because I don't want to waste my spectrum. For that, here spectrum is nothing but channels. So you should not waste that spectrums. The spectrum also there that will occupy by any customers. Okay, first they give priority to the primary customers. If any space is available, immediately you will try to give the service to secondary users. That's the idea of this. So secondary user license can dynamically access the channel for transmission of the packets. Each channel can handle either one primary packet or one secondary packet. For each channel, handle only one primary users or secondary users. That's what a model describes. Packets, primary packets have high priority over the secondary packets. As I told you, because they are paying to get the service, so we have to give the priority for that. Okay, primary users. Okay, whenever server is free and it's not occupied by the primary users, then secondary user can occupy without paying money. That's the idea of this. Okay, here this. So the money is playing vital role everywhere. Okay, right. If one of the C channel is ideal at the instant of arrival of primary secondary packet, the transmission of this packet begin immediately. If one of the channels is free, then immediately the head of the customer in the queue will occupy the server. That's the idea of this. Okay, and begins immediately. On the other hand, if all or few of the C channels are occupied by secondary packet, and the remaining channels are busy with the primary users for the transmission, the arriving secondary packets line up in the buffer, as I told you. If all channels are busy, then queue will be found for secondary users. That's the idea of this. Okay, lines of the buffer of the unlimited capacity with the probability 1. Okay, for its transmission, later based on the first come, first service. Of course, secondary users are served by first come, first service. That's the idea of us. But the primary users, if I occupy all the channels by primary users, the generated new primary user cannot occupy server, you will go to that orbit. It will be blocked, go to orbit and keep trying to get that free server. Similarly, another premise is generated if all servers are occupied by that premises, again you go to that orbit. From there you keep trying to occupy that free servers. Free server means free channels, that's the idea of this. Okay, this is what the model I have that. So whereas if all channels are engaged with the transmission of premise packet, the arriving secondary packets may either line up or secondary waiting line buffer with the probability B or leave the system forever without completing service. You may join, okay, or you may leave without getting service. So balking also introduced. Next, please. So after successful transmission of secondary packets, this packet leave the systems. So after getting that successful service, the secondary users leave the system forever. That's the idea of this. In addition, the transmission requests from the premises are generated by finite number of homogeneous source of size n. As I told you, premises are generated by finite source. Okay, so not more than n primary users. Okay, if all channels occupy the primary users, will block, will go to that orbit. As I told you, from there it will try to get that free channels. Okay, like that. Once it gets that service, you go to again that where that finite source. So number of finite source size is n. That's the idea of this. Okay, each of these sources in the free state, that is, it is not being transmitting or not in the orbit, may generate a premise packet to access the channels independently of any other source in the free state. Parallel process of new premise packet is a quasi-random because parallel rate is lambda into n minus k. K is already in the orbit or with the server. That's the meaning of this. Okay, the remaining will be n minus j in the finite source. That's the idea of this. Okay, please. So upon the arrival of premise packet, its transmission commences immediately when at least one channel is ideal. On the other hand, if the secondary packets occupy some channels, then and premises occupy the remaining channels, so that all C channels are occupied by premises and secondary packets. The arriving premise packets interrupt that one of that, because some of them occupy the primary users, some of them occupied by secondary users. The new primary users generated, then you will push that the secondary users in the server to where the end of the line of the queue, then this customer will occupy. If all channels are busy with the primary users, it will block, go to that orbit. The primary users. This is a model we are making actually. Okay, right. So hence the transmission of secondary packets is started. Once one of the service interrupted customers will be get service if one of the service is free. That's the meaning of this. Transmission time of primary packets follows exponential distribution. I think full screen is not coming. The protection was missing. Okay. Okay. Can you able to see? Okay. Only few items, no problem. Okay. That is right. Please do. I'm sorry. So just know the way you have to manage with that. Here that retail rate new, the j customers in the orbit is a random order, so j into new. We have this. Any one of them will keep trying to occupy free server. That's the idea of this. Other things are working. Next slide, please. Model, you know that the service rate of the primary users are mu1. The service secondary users rate is mu2. They are exponential. Therefore, mean is 1 by mu1 and mu 1 by mu2. This is the idea of this. Okay, right. Next slide, please. So they are competing. How many customers are there? Can you remember who are competing for that servers? From that finite source, from that orbit, same primary users, from that secondary users. So that's what is the competing among that this one. So the rate of primary users, okay, generated by primary users from that finite source, this one, and this is retail customers try to occupy the channel, and lambda 2 is new customers from that secondary users queue. This is what they try to occupy that channels. This idea. Next slide, please. We are going to talk about the 4-dimension random variable process. So here N1 is a number of customers in the queue as well as in the server, and total number of customers in the system. N2 is a number of customers in the orbit of primary users, and S1 is a number of customers of the secondary users occupying that servers, and S2 is a number of primary users occupying the servers. So this is what idea of this. Okay, so N1 is a number of secondary packets in the system, including secondary users packet being served by the channel, and N2 is a number of packets, primary packets in the orbit, and S1 is a channels being busy with S2 packets, and S2 is a number of channels busy at transmitting primary users. Okay, this is what your state case for your 4-dimensional random process. Okay, state case here I is the number of customers in the queue. Okay, of course the secondary users. Here is the number of customers, the primary users, and of course L lies between number of customers occupied by the secondary user channels, secondary customers in the channel, and of course the minimum of this one we have this. So this are all I described actually. So very tedious problem to make it that matrix. We are making that one. So this is the idea actually. Okay, next slide please. First we can actually microstate we introduce. So these are based on that total number of customers in the system. So this we have to explain a lot. So time will take. Please kindly bear with me. There's no other way. Okay. So there are 3 cases: K plus L less than C, and of course K plus L equal to C, and K plus L greater than C. So 3 cases we are going to discuss. Now I say that level is nothing but number of customers in the secondary users in the queue. So that's a level I. I means no customer in the queue, 1 customer in the queue, 2 customers in the queue. That's a level. We are saying that based on that secondary users customers in the queue. Okay, here this. So I can say that this is a level I when K plus L less than or equal to C, and K plus L is equal to C, the level will be this I is equal to this one, and next slide please. So these 2 cases, then this is what your Gaussian-Barton process matrix. Look at that, each one is a matrix, and this is a cluster matrix, not single matrix. Matrix, within that matrix, we have so many matrices. That's the idea of this. It's not so easy to get that one actually. Okay, so computations take a lot of time to get your results. Okay, that's the main thing actually. Because matrix jump solution means computations. Without computation, no matrix jump solutions. That's the idea of this. But we complicated the problems and get that to use that for real world problems. That's the idea of this. Okay, so we have that right angle matrix. So Gaussian-Barton process. So we have to shift that little bit. Okay, next slide please. See that BSC. Take the diagonal matrices. You take any one of the diagonal matrix. Next slide please. That is again written as in this manner. The diagonal matrix, one of the diagonal matrix, I can written again right angle matrix. Okay. Here also the diagonal matrix. Okay. Again you are partitioning further diagonal matrix. Next slide please. So that's what I'm saying. So each matrix actually is cluster of matrix we are discussing. So that's a very tedious problem, but now people are expecting this kind of problem only for research to publish in good papers, in good journals. There's no other way. Because we spent more than 1 year to construct that matrix and do that complete work. Publication take another 6 months or 7 months. That's the idea of this. That's if you want to publish in good papers, in good journals. There's no other way. And without paying any pay charge. Underline it. So far I have not paid any pay charge from my packet, which I don't like it. My knowledge you should not sell to others. Similarly, I review the paper if it is not article cost charging channel, like journal. If they are charging article cost, I'm sorry, I can't do it. They are earning money, why should I do for that work? And the quality of paper is won't be very good. That's the main thing actually. So that's why I always publish the paper without article percent charge. Also review the paper is coming from without article percent charge. That's what I'm interested. Okay, because I'll get knowledge. If it is such a paper, get it, I'll get knowledge. If your article process judge means, I'm sorry, I don't want to disclose anything. Okay, this one. So these are matrix actually. Next slide, please. Similarly, the other matrix, each matrix you can write it in this manner. The cluster of matrix I'm writing. Next. Now, this is actually A1 matrix that appear in this Q matrix. Again, the tridiagonal matrix. This also you are splitting diagonal, upper diagonal, lower diagonal matrix. Further matrices, several matrices class. Okay, partition in this manner. Next line, please. So that's what I'm mentioning. The further partitioning. Next line. Okay, this is what I'm writing. Okay, so what are the matters? Next. This is of course over diagonal. Over diagonal means upper diagonal, diagonal matrix, and lower diagonal. I'm defining in this manner in terms of matrices. That's what the diagonal, diagonal plus, diagonal minus stand for diagonal, over diagonal, sub diagonal matrix whose entries are listed in the brackets. That's why I got this. Next, please. So this is what your A2 matrix. Okay. Next slide. We'll come to the main part. This is a matrix again. It's up in the Mercator process. Next slide. So I want to get that stability conditions. Okay. News has introduced what is how to get the stability condition. You know that adding that repeated portion A0, A1, A2 minus level independent process. Easy to get that stability condition. If it is level independent means very tedious to get done. You have to use a Bowman algorithm that also we introduced in the call center columns which appear in the pathology computing applied problem. Springer joints. Okay, so you add that one, then you get the stability. This is an invariant matrix. You can find the invariant probability for that matrix H. Okay, next time. So that invariant probability you can partition like that. That satisfies these conditions. These are normalized conditions. Phi of A is equal to 0. Normalized condition satisfied. Okay, you can evaluate what is that phi. Phi is important for us. Once you have that phi, okay, you can get the stability condition like this. So you can choose the parameters based on that stability conditions. Okay, because you have that impedance capacity for the secondary uses Q. So we need stability to stable that. Okay, to make a stable the Q size, we need a stability condition. That's why we're discussing stability conditions. Next slide, please. Okay, system. Now I want to talk about what is system size. So far we talked about stability conditions. I'm going to talk about stability conditions. That is also sort of vectors. So each vector is a probability vectors. Okay. So x of t is this one, and this is a we steady state probability vectors of generated. That for that Q is an invariant matrix. So you have to find that invariant probability for that matrix Q. That satisfies this condition again. Is okay. We have this. Next slide, please. Clearly, each x is a row vector of dimension, this one, and it can be partitioned according to state arranged in the state space. So we arrange it again the state space of each vector xi. So it takes a lot of time to explain. Next slide, please. Suppose that when there are three cases, previous slide. The previous slide is here A plus L plus C. Of course, I is less than C. That's the two cases we are discussing. We are partitioning I less than C. Next slide. Next case is I greater than C. I greater than C. There are two cases we have to discuss. Okay? So these are all that vectors satisfy these equations. Okay? The boundary equation. This is of course repeated portion equations. Of course, R is a square. Okay? Matrix satisfies the this one quadratic equations. Quadratic equation. Okay? Of course, should be equal to 0. That should be 0. 0 is missing. Please kindly have that one. Quadratic equation. X equal to 0. Okay? That's value of quadratic equation. Getting that R is very tedious. Okay? Explicitly. So, numerical work will help us. The main idea is what is that? Logarithmic reduction algorithm or cyclic reduction algorithm. A Bowman algorithm you can apply. There are so many algorithms there actually. Okay? Any other algorithm you can apply. Get that. But generally, a level independent, you can use that logarithm reduction algorithms. That's the idea. Okay? Right. Next slide. This is the normalized conditions. So we need to always normalize the condition. Check whether some of the probability should be 1 based on this. Because we are talking about the homogeneous equation. To get a non-homogeneous equation on the right hand side, we have to include that normalization conditions. To make a normalized condition, then only get the non-homogeneous condition, then only get a unique solution. Otherwise, you get an infinite number of solutions. Meaningless. So you want to always include that nomination conditions. Next please. I told you A0, A1, A2 are highly structured, getting that explicit expression R is so difficult, but in numerical you can forget that I have done it. Okay, so we apply all, once you know that all the probabilities, okay, and R, okay, we can get for that steady state probability vector for that systems. That's the idea of this. Next line please. System performance, very important things actually. First one is system is empty, second is packet, that means what that, this one is the queue is empty, second is the queue is empty, that you can obtain. The probability of primary users, okay, what are the channels are busy and transmitting from this packet. The probability of primary that all channels are busy, all channels are occupied by primary users packet. That's the probability. We have this, okay, right? Then next, the probability of primary users that all channels are busy by transmitting. All channels are occupied by secondary users. First one is all channels are occupied by primary users. All channels are occupied by the secondary users. Then last probability, because may or may not join. If we not join means 1 minus p, join means p. So last probability I can get it multiplying that primary users packet probability by 1 minus p. We get last probability of secondary users. That's the idea of this. Next, of course, the probability of ideal channel, that is x naught into that vector that I defined here. Okay, the loss rate multiplied with lambda with that loss probability, you will get that what is the loss rate of the secondary users. The throughput, that's one of them. There are two things are important in the queuing theory or any computer communication system. One is throughput. The output, very important point. How fast is working? So throughput is very important point that you can calculate for this model. Another one is waiting line. Okay, that is also very, how long you have to wait. You want to always optimize your waiting time. For that you have to make a system in this manner. So okay, so waiting time and throughput are two important performance measures. What are the communication systems or queuing models? So of course, all communication systems are modeled by queuing systems. Based on that only, they are doing that estimating that what are the performance measures for the systems. That's the idea of this. That's why the performance are playing vital role. Okay, the queuing models for the computer communication systems. That's the thing. Next, of course, expected number of customers in the orbit. Okay, and expected customer in the secondary users line. So those things you can obtain once you know that are that steady state probability vectors. You get it. Next line. Of course, the mean arrival rate of primary vector is this one. Okay, here C is missing. I have to put C here. Sorry. Then expected waiting time of that orbit. Okay, this is what we have. Expected waiting time of secondary packets in the queue. This is what the expressions. Okay, two performances I told you, throughput and waiting time, very important things for both primary users, secondary users. That's the idea of this. Right. Next line. Of course, optimal rate. Suppose all servers are busy, only one server is free. Then the retail customer try to occupy the primary, that one of that free one. Then if it occupy that one is only one is free, it is free, then you try to occupy all servers are busy. That's called an ideal retrial. You are making all customers are busy. That's called an ideal retrial. Try, you get that one server is free, occupy. Now it makes all servers are busy. That's called an ideal retrials. Okay, next one. This is main retrial. All servers are occupied by primary users. Then from that orbit, try to occupy, but already all the customers are, all the servers are occupied by primary users. You cannot occupy, again come back to that one. Mean, wasted this time to try to get that service. That's a main retrial problem. Next, successful retrial. So, if one of the servers is free, or some of the servers are occupied by secondary users, some of the customers are servers are occupied by primary users, you go push that secondary users to that line, head of the line, you will occupy. That's called successful retrial rates. Okay, these things performances are very important in the retrial queues. Many of them not discuss this one, only few of them discussing this kind of things. Okay, especially this model they are not discussed. This kind of coordinate networks they are not discussed. Next slide please. Of course, next one is first pass at time. See, there's a queue forming the secondary user packets. Okay, then if you cross certain level, system will be collapsed. To avoid that one, you have to control second user packets. Already I implemented what is that bulking probability. Apart from that, I want how long it will take to reach a particular level L in the queue. Okay, that's the first pass time reaching that size L. If you measure that one, that system manager can easily guess. So when should I stop the new arrivals to the systems? So this kind of performance measures are very important. So far we talked about discrete state-based continuous time. Now we are going to talk about continuous time, continuous state-based. Time is continuous. How long reach to size L? The first pass time to reach size L that we are going to discuss. That's a very important performance measures. So for that, I am defining that first pass time to reach the critical level L. Okay, the run variable. Next, of course, corresponding conditional Laplace transform for the run variable and the corresponding ortho moment for the t. Okay, this you can partition in this manner. Okay, yes. Next slide, please. You can partition like that. Next. And here partition the moments also get it. Next, you can put it in this manner. If not, this next slide, please. The sorry is actually forcing me to finish. So this is identity matrix. Of course, this one I have. This is what a truncated matrix up to level. We have that. Originally, we have that infinite size. Now we are truncated up to L. So automatically, you will get the finite size Q. Next, this matrix to attain. You have to use a first step analysis. This technique nowadays not using south side. Well, if you are using this one actually. Okay, first step analysis use it, then you can argue like this. So from here to that, where it goes, I mean L2, L plus 1, or L2, K, I plus 1, or K plus 1, like that. So you can argue in this manner, you will get that one. Okay, next slide please. So this is what a first step analysis, this itself is a separate problem, but we clubbed all together for this model. That's idea. This idea I am using here. Next line, please. Next line. Next slide, please. Okay, next slide. So we have three cases: I is less than C, I greater than C. Those things I discuss. Okay, time is limited. Oh, next slide. Okay, next slide. So you can put this. Next slide. You can put everything. Next slide. Everything actually. In this manner, the initial conditions that satisfy these equations. Satisfy the equations. Okay. Differentiating this one, that means satisfy these tridiagonal systems. Next. This, using that Leibniz rule for product of two factors, you'll get that mean. Next slide. Of course, this is what the inverse you are going to get it. First moment, second moment for that how long it will take to reach the size L, particular L. Okay, the mean of that one and the second moment of that one, and variance also you can append once you know the first two moments. Next point. Of course, this are a graph. For example, what is that? Mu is a retail rate. If the customer from the orbit keeps retrailing and occupies the server, obviously the primary user, the second user customer will loss, will be increased. Because all customers occupy the primary users, then new customer cannot join, or the second user, the customer will be lost. Like that, we discuss several things here. Next slide. So many times, okay, these are like that. So last properties are different. So to a new will be physical definition there, not just like that draw. After plotting that one, I give that why it is like that. What is the reason? We explain everything in this. Next slide. Next slide. This is throughput. See, when new increases, all customers of second users will be blocked. Throughput will be reduced. You cannot come out. See, if you get service of secondary users, you leave. If it blocked, there is no chance of leaving the system. That means it will be blocked. So throughput will be reduced. If the primary users occupy all the channels, so that's why it is reduced. So like that we discuss. Next line. Of course, throughput increase if more customers join in the queue. Increase. Next. 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 So, okay. Waiting times also we discuss. Okay. Waiting time normal waiting system. Waiting we discuss. Next. 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 Of course. See the identity chain. We start up. ideal rate is shorter. If the number of servers is less, it will take quickly to take the maximum value for the particular view. If the number of customers increase, onset delay to make that maximum value. So basically, mean will fail. This is a successful return because if all customer occupied at the RPT customer, okay, occupied the new customer, again that new customer can already all servers are busy with the primary users. New customer from that RPT cannot occupy, then it will automatically decrease. Occupying the 10th floor will be decrease. That's the minimum. Next. These are some references, and of course we made a table. Okay, made a table for the first class time. Time is limited. I'm sorry. Okay. These are some references. Of course, Attalango. Never forget about him. He loves Indian. Okay, especially South Indians. He started with a fight. Really, once he came to his friends, okay, to Cochin University to attend the conference, one of the Indians actually present his work in front of him. Ditto. I don't want to mention his name. He was shouting, "This is my work, this is my work, my work." He didn't bother. He presently left. Okay? This is just a telling actually. Then he had a bad opinion about that Indians. He went to Spain, of course, Madrid. So, went to Madrid, then I wrote a letter. So, I would like to get your reference, more helpful. He sent a mail. Not mail, no, just no mail. That time very difficult to mail them. He sent a letter, airmail. But before that, he sent a letter to everybody. His abstract, person who presented the conference abstract, ditto to everybody who attended that conference. Everybody sent it actually. There are certain people that said, "You are doing this kind of work. How can you send it by reference to you?" Then I got angry with him. Look, even not the letterhead. Therefore, shit. If you are interested, you send it. Otherwise, okay, don't think all Indians are doing this kind of nonsense things. I wrote it like this. If you are interested, you send it. Otherwise, forget about this letter. Only A4 6. Immediately send a bunch of things. From that onwards, he was best friend of Indians, especially me. 3 times he called me for the Madrid conference without asking any single paise. Okay, he provided all the expense except that airfare I got from the Chennai University, CSR, MBHM, the DST, everything. They are paying after seeing my biodata immediately begin. So, airport, if he once landed, he will take our group to hotel free of cost, everything free of cost, provided accommodations, okay, conference trips, sightseeing, right? 2010, 2002, 2006, 2010, okay, all 3 conference means what? Not like this. So, queuing there, Madrid conference queuing there, MCQT, I mean, not like means not mixed group, only probability group, I mean, especially queuing theory only. They are actually wrote so many thousands of papers, they wrote so many books, okay, they are pioneer worker, okay, they produced so many PhDs, they have written so many books also. So, such a people are sitting in this hall, you have to present, because Ramaswamy was also there. So, he said, our Enga Oorkaran present pandran, na attend pannom, I don't want to charge this section. He left his charge section to the other friend, he was sitting and give nice comments about our work. But whenever I go abroad, I will prepare very sincerely to get name. Name is important. Okay, that's important. So, that's what I am telling. So, if you work hard, definitely you will get everything nicely. You will come up quickly in your life. That's what I want to say. Why I am telling? So, then after that he became friend. Whatever help I required, immediately used to do. So, if you come to Chennai, you stay with us, you enjoy, was cooking. Most of that foreigners like South Indians than North Indians. I am sorry to say this one, that's no other way. Our way of hospitality is they like very much. Okay, seriously. Thank you very much. Thanks for our chairperson. Okay, and audience. Even though few of them, somewhat I could give that information. you take it as a base and try to work it out. Of course, I thank Professor Vittal, our friend Karthikeyan, okay, having invited me to deliver my talk. Okay, thanks all. Okay, thank you very much.